Brigham Young University, and he does some fantastic work in compliant mechanisms and origami. So he's going to talk about what he's been doing. And so without any further ado, Mr. Howell.
All right, thank you. It's great to be here with you. And first, I'll just note some of my faculty colleagues here's work that the show has been together. And Robert Lang is a really interesting guy. He's a full-time origami artist. You know, a guy that can actually make his living doing origami. Okay? But he's a unique artist in that he also has a PhD in applied physics from Caltech, and really does a lot of the mathematics. If you get a chance, go watch his TED Talk. It's called The Math and Magic of Origami. So in 18 minutes, and you'll be blown away. So, all right. So, just a little bit of background on our group at BYU, Compliant Mechanisms Research Group, and our mission is to make an impact by creating compliant mechanism theory and applications that are novel, used by others to make a difference for good. So hopefully as we go through this, you'll kind of see this theme of this, creating the theory, and then also taking that theory and demonstrating how to use that in applications. And first of all, so a compliant mechanism is a device that gets some or all of its motion from the deflection of its parts. So here's the traditional rigid body mechanism, right? This is a parallel guiding mechanism where you have, those two links have the same length as those two links, and this bar, anyway, the opposite side bars are always parallel to its opposite member, okay? So that's, but it has pin joints and other things, so a compliant mechanism then is something that could get that similar motion, but now do that with compliant members. Okay, so that's a very simple version of this parallel guiding mechanism, and you can put these together and show that, yes, they do have the same motion, but now we have lots fewer parts. And similar thing here, now we can also show, so we got beat up in the flight here, but another version of that, okay, of a mechanism, but now it looks a little different than the other one, but has the same kind of motion. And again, we can, this has been designed in a way to make it so that the motion is the same. And if you look up close there, you'll see that that's those have equivalent motion. We use something called the pseudo-rigid body model, which is a modeling method that helps us convert between compliant mechanisms and rigid body mechanisms. All right, so what are some of the advantages, you think, of a compliant mechanism over a traditional rigid body mechanism? What are some reasons why you think about doing that?
Less parts.
Okay, fewer parts. Okay, it's a big deal. Okay, for a lot of reasons. Okay, what else? What's that? Yeah, no joint slop. So here, I have to maintain some kind of clearance, right? Because my pin has to be smaller than my hole, or I end up with a press fit. And with that, we get some backlash, and that results in some sloppy motion. Okay, and so if you were to go in to a clean room or something and tear the high precision equipment apart, you would find lots of compliant mechanisms in there. Okay, because you have to have really, really high precision machines. Okay, what else? What other advantages? We'll talk about some challenges or disadvantages also in a minute. But what are some other advantages? Got part count. Got okay, low friction. Yeah, so I don't have any rubbing parts here, right? So I totally eliminated all that rubbing friction, which could also mean I get rid of things like lubricants and other things, okay? There's something else back here? Okay, all right, so yeah, so we can simulate this motion of things really well, okay, and then the microcontrollers, the microsystems. Also, or say micro, right, we can also go to very small scale. So we did a lot of work in MEMS for a while where this is really hard to make at the microscopic level because you can't assemble parts, but that we can make out of a single layer. Okay? All right, so there's some good advantages. We'll maybe chat about some others as we go along, but one and another one, or anyway, any others before we move on? Advantages.
Better mechanical advantage in a small compact form factor.
Yeah, you can get some very high mechanical advantage and high, some very nice compact forms. Okay.
Is it maybe possible to exploit thermal sometimes?
Okay. Yeah, you can exploit some thermal properties at times. Okay. And
it can absorb external forces because it's...
Yeah, okay, you can absorb external forces. So related to that is this idea that you can have I can combine the function of both the pins and the spring, right? This has a return to home position that as if I had springs. So that may be a plus or a minus, depends if I want it or not, right? So that has a return to home position. I'm replacing both the pins and the springs. Okay, so that's that could be an advantage or a disadvantage. All right, so there's some reasons why you might go there. I'd also say that you can also tailor the forces really well, which is another thing. So you can make things at all kinds of size scales and other things. All right. What are some of the challenges going from rigid body mechanism to a compliant mechanism?
They allow quantum motion.
Yeah, what's that?
Compliant mechanisms allow unwanted motion.
Yeah, especially let's say I say, oh yeah, that's a nice motion, but what if I put all the load this way? Right? It can buckle and give me some some undesired parasitic motion there. Okay. Other disadvantages or challenges. Okay, yeah, we have to worry about yielding, okay, and a lot of the compliant mechanisms you see in the world that are products actually do yield on purpose, actually. When you put ketchup on your hash browns, especially you guys had muffins, you didn't have ketchup on your hash browns, but anyway, but you flipped open that lid, right, that polypropylene's actually yielding. It's beyond the elastic limit, polypropylene, but you're going through so few cycles on that in its life, a few hundred cycles at most, and it turns out that it still survives it. But other times, you're not going to be able to do that, right? You have to watch the material properties and everything. Okay? Any other challenges? Okay, you hit some of the big ones there. The other thing is, when one of these pieces break, I might be able to replace one of those pieces. And I don't have that advantage. When something breaks here, I may have to do the whole thing. All right, so there's some advantages, challenges. And I'm going to tell you just a couple key things about compliant mechanisms that if you can, then I want to move on to origami, okay? But here's the key principle. If you remember this and understand this, everything else will make sense, okay? But whenever you've designed things, mechanisms or other things, you've almost always wanted something to be both stiff and strong, okay? When you've done that, okay, so imagine an aircraft wing or a landing gear or a connecting rod in an engine, whatever. You want it to be both stiff and strong. And what's happened is that you have become, in your mind, you've developed an intuition that tells you that stiffness and strength are the same thing. And because you've always wanted them at the same time. Okay? And here is the key. Stiffness and strength are not the same thing. Okay? They are not the same thing. Okay, so if I could jump on a table and scream that, my head would hit this low ceiling up here, okay? That is the point. Your intuition has, because you've wanted them at the same time, you have begun to think that they are the same. Stiffness is a property related to how much something, or its resistance to motion under load. Okay? Strength is how much load it'll take until failure. Those are different things. They're also related to different mechanical properties, right? Young's modulus related to stiffness, strength, yield strength, ultimate strength, things like that related to the strength. So because these are different, it is possible to make something that's both flexible and strong. Okay? Now, most of the time you don't need to do that. Most of the time you're trying to make something both stiff and strong. Okay, so 95% of the time that you design things in your life, that's going to be the case, unless you want to do something that's a compliant mechanism. And then you need to understand this. So this takes me about a week of lectures and graduate course to pound this into the students, right? We have to go through all the equations, all the derivations. Turns out we don't have a week, okay? So you guys have to be smarter than that. Just get it right there, okay? Stiffness and strength are not the same thing. You can make things both flexible and strong. Okay, so I once wrote a book on compliant mechanisms, okay? And this is how interesting that book is, okay? And in that book, I talk about the advantages and then the challenges of compliant mechanisms. And one of the challenges, they say, well, a compliant link cannot produce a continuous rotational motion. Okay, that's obvious, right? I cannot, what you guys were doing here, right? You can't hook up a compliant link onto this motor and have continuous revolution. It just doesn't work, right? And so that's one of the challenges. You don't need to prove that or anything because it's just obvious. Well, it turns out no one bothered to tell the paper artists that, and they created a compliant mechanism with continuous rotation. Okay, that's called a kaleidocycle. Is that not freaky? Okay, I've seen this a lot and it still freaks me out. Okay? Okay, so those of you that want to go do the kinematics, you'll see that this is a car with 6R. Okay, if you put a joint where every crease is. Okay, so but still that is pretty fascinating. So we start to see that when we start to look at this origami stuff, that there is some interesting things that we probably would not have found in our regular mechanism design. So you start to see some interesting shapes. Okay, so this is sometimes it's called the brick wall. Okay, and you see some really interesting motions here. And that's just one sheet of paper. Okay, and or let's see. Yeah, so similar kind of thing here, and you see that twisting motion that happens there in this guy. Okay. So there's reasons why we should go look at origami and understand a little bit better how this works. And there's first, before we do that, we want to learn some basic terminology about origami. Okay. So let's got 3 PhD students back here that are going to help us pass these out. So this is also, if we're done with this, if you want a PDF of this, it is it's online on the course resources. Let's see. Okay, so if you'll, some of these pages, these are stapled together. We'll just be ripping some of these pages out here in a minute. Okay, just got a cover page. Then the second page, okay, looks like this, just has some terminology. But what we're going to do is we're going to use the next page. Go to the third page, one that looks like this. Okay, go to this third page and rip that page out. And we're going to learn that, but then turn back to the second page where it has that terminology, okay? Where it has some important terms, okay? So you should have this page ripped out. Okay, we're going to teach you some really basic origami terms here. First of all, we're going to fold this. Don't worry, this round box, gray box is where sometimes we'll cut these out. We're not going to do that. We don't need to here. Okay, but just go ahead, see that crease, that line that goes between blue and red dash. Just crease that right along that line. And if you want to get a really good crease after you crease it like that, just use your thumbnail and go across like that. Okay, get the crease really good. Then, okay, once you have that crease, I go ahead and just flip it back the other way. Okay, and crease it that way. And then crease it back over here. Okay, so now you have a folded, that's folded in half. Congratulations, you folded a sheet of paper in half. Okay? All right, now, see this blue line there? That goes across, because it's symmetric, we're going to be able to fold that. And just fold it along, to get a crease along that blue line. And again, make that, use your thumbnail or whatever, make that, or use what's called a folding bone. Okay, a folding bone is just anything you can use to press up against it, okay? And you can actually buy a formal folding bone, or you can just use your pen or whatever. Okay, and then it makes it easier if you flip it around the other way, okay, and do it both ways. Okay, so now if you unfold it, now what we're going to do is we're going to introduce some terms here. These blue lines we're going to call mountain folds, which means they're going to be poking up. The red dashed line we're going to call a valley fold, and it's going to be down. Okay? So what you're going to do is you're going to push that red line, and that's why we folded the paper back and forth, right? So it'll make it so we can do. And what you're going to do is you're going to make that go like that in there, so that red line becomes a valley fold. Okay, so there we have your first origami vertex. Okay, so let's introduce some terms here. Okay, the blue line, what do we call that? A mountain fold, okay, and there's a valley fold. Okay, when we look at that sheet, that's called a crease pattern. Okay, that's the crease pattern. If we define the valley and mountain folds, we call that an assigned crease pattern. Sometimes you have a crease pattern that just shows the creases, and then this is an assigned crease pattern, meaning that we've assigned both the mountain and valley. Now you also have to remember it all depends on your point of view, right? Suddenly, if I'm looking at it this way, all my mountains are valleys and my valleys are mountains, right? So it is all a matter of your perspective there. Then, where we had all of these things come in to one point, that is what we call an origami vertex. This is a degree 4 vertex because we have 4 creases coming into one point. We can have other vertices, okay, but this is degree 4 vertex. We're going to see a lot of those. And then here we have a facet. Okay? And let's see, what other terms here? I forget. Okay, flat foldable. This piece of origami, we can fold flat like that. That makes it flat origami. Okay, flat foldable. Okay, not all origami will do that, but we did that here. There's also what we call rigidly foldable, which means that if all of these panels were stiff like steel, and the only place I had motion was at the creases, then that would be rigid, and it still moved, that would be rigidly foldable, or rigid foldable, okay? And one last term, oh, and then of course this is the vertex where they all intersect. And then there's something called action origami. If you fold something, then it becomes like a flower. Okay, that's not action origami. Okay, it just sits there. Now let's say you fold something and it becomes a Venus flytrap, right, that moves, that's action origami. So this, okay, you can, if the reason you made it is for that motion, then that is action origami. Okay, and okay, any questions on that? Okay, now we're going to fold just a, let's see, how we're doing on time here. Let's skip this guy. Okay, you can come back that and fold that one at your leisure. Okay, and now let's rip this one out. It's the one with just the dot. All right, now this is going to be a little exercise where you are going to create your own flat foldable vertex. Okay, but that dot is going to be the vertex. Okay, and then we're going to come back and we are going to see what everyone did. And we'll try to find some patterns here. So what you'll do is you can, right? They have to. Last time we did a symmetric vertex, right? It doesn't have to be symmetric. So here's one where instead of going all the way across the paper, I'm just going to go like that, right? And then I might have another one that does whatever. Okay, you're going to fold, just fold this however you want, and then we'll come back. And when you want something to come into a vertex like that again, you just come in and pinch it at that point. And don't worry, just, you know, it could just be crazy. Matter of fact, if you just want to get it, you know, make some formal folds and then kind of smush it into place, that's fine too. As long as it's mostly the vertex. You can have as many creases as you want. You can have, and then we're going to see what kind of vertices that we have there. The only thing I'd say though is it should be flat foldable when you get done. All right, how are we doing?
done.
Okay, so now what we're going to do is we're going to see if we have any patterns here that we can identify. And okay, so I did mine. I did had a total of 8 active creases. I had, as I counted up, there were 2 mountain folds and 6 valley folds. Oh, no, sorry, that's not right. What did I do? Let's look at the first one we did. Where did I put it? In the that first one we did had 3 mountain folds, right, and 1 valley fold. Okay. Okay. What else? So, and when we talk about the creases, they need to be active creases, meaning if I folded something and then in its flat state it's no longer folded, then we don't count that. Okay. And okay. What do we have here? Who can tell me how many mountain and valley folds they have? These 3 guys will help you.
10 and 8.
10 and 8. Okay, so we have a 10 and an 8. Did I hear something else?
Oops. 4 and a 3.
Okay, 4 and a 3. Okay, somebody want to check Dr. Agrawal's thing here?
Where? Bias.
Okay, we got a 4 and a 2.
5 and 3.
Say that again?
5 and 3.
5 and 3. Okay. So it's very common here. I surprise. Usually, what happens is we get more. We have to double check. Okay. It has to go all the way flat, and the crease has to be creased at the time when it's flat. Okay? Anyone else want to be brave and tell us what you got? What was that? 10 and 8 again. Okay. 8 and 6. Okay.
4 and 3.
What was that?
4 and 3. He's already there.
Okay. All right, Brandon, can you come check this one that was 4 and 3?
It's not true.
Thank you.
Good. All right, what did you get?
4-2.
4-2. Okay.
This one isn't actually completely flat.
I started to count mine up here, and then I got the wrong number that was infeasible, and that's what I had to do.
It's not actually.
So, oh, wait a minute, what did I do?
Four and two, Dr. Howell.
4 and 2. Okay. Okay, I've got a. Okay. All right. Okay, this is enough for us to find the pattern here. Okay, and I had, when I look at this one again, I have a 5 and 3 here. Okay, what we find are some interesting properties here. What do you notice about that pattern? What do you see?
The number of one-dimensional pieces.
Yeah, the number is always there's a difference of 2 between the number of mountain and valley folds. That is always the case for a flat foldable vertex. Okay, what else you notice? If you sum those 2 numbers, what do you get?
Not an even.
You always get an even number. Okay, so these that is 2 theorems. One is the Kawasaki theorem, and one is the I forget, Malachi's theorem. Okay, and so so there's also some other interesting properties that come about. If you find the smallest angle in that vertex between any 2 lines, you will find it is always bound by a mountain and a valley fold. Okay, always. Okay, doesn't matter how many degrees it is, the smallest angle will always be bound by a mountain and valley fold. Okay, so that's gives us some interesting, so you start to get a hint that there's some interesting mathematics and stuff buried in origami. And okay. So let's move on here. So there's a lot of interesting research that we can do here, and of course the big one is all the mathematical modeling. Is how do we model these systems? We already hinted to some of this. Is if you take those creases and you treat those as if they're hinges, then you get a spherical linkage. Yep. If all those hinges come in and intersect at a point, that is a spherical linkage. And where'd he go? Mike McCarthy, who you just was here, he's and others, right? He has a book that we go to all the time on our spherical linkages. Okay, so so there's a lot of interesting things there. And then imagine now what happens here. Is I just have a vertex. What is that? That is a whole series of spherical linkages. That going to make for some really interesting mathematics, right? We've not, this advantage of going and seeing the origami is now you say, oh, wait a minute. I'd never thought of putting all those spherical mechanisms together in some crazy array like this, right? Or like this or whatever. Okay, so there's some really interesting mathematical problems. And again, go watch Robert Lang's The Math and Magic of Origami, his TED Talk, and you'll see some more of that. Okay, rigid foldability. We already talked about this. This is now really important when we start going to systems that are engineering materials. And thick. Okay, when we folded this vertex, okay, we made the assumption we're using paper, and it turns out paper is paper thin, okay, and we can neglect the thickness there. Now, if those are steel panels or titanium, suddenly I can't ignore that thickness, okay. Then we have something we call surrogate folds. And that is, again, going to our steel or our titanium type analogy here, if we're trying to move to other materials. This piece of paper, I can crease right there. Yes?
I was just suggesting if you can stand here
Oh,
so
sorry.
the camera can capture it too.
Okay,
Maybe it's
alright.
on the side.
Okay. All right, so if we have this piece of paper here, okay, and I can crease that. And the thing that happens with paper, if you go look at that under a microscope now, you'll find we just delaminated the paper. Okay, it's a bunch of fibers and stuff, and we just delaminated at that point, and we have made it more flexible at that point through the delamination. What happens now, if you go home after this, and you go into the kitchen and get some aluminum foil that you use, and you crease it, and then you fold it back like this. You know, since this is more flexible there, we've delaminated it, and it turns out that it tends to want to crease at that, to move at that point. If you do that in aluminum foil, what did you just do to the material?
Deforming plastic.
Yeah, you work hardened it. You made it stronger. You made it stiff. Actually, the same stiffness, but you made it stronger. Okay, and you did not change the stiffness. It will not go at that point. Matter of fact, if I take that, because you strengthened it there, the next time you go to crease it and it will want to yield, it will actually yield next to that crease, not at the crease. Okay? So paper is a unique material. Okay? And there's Tyvek, which is a synthetic paper that's a polymer that actually works well too. But it's pretty unique. So we need to find ways that we can get our motion. And here's one way to get what we call a surrogate fold, a replacement fold. Okay, so now we have that. This material, this is acrylic, which is very brittle. Okay, that's another thing. Brittleness and flexibility are not the same thing. What is brittleness?
Tendency to break.
Yeah, how it breaks, right? When it breaks is catastrophic. Does that say anything about its flexibility before it breaks? No. You can make things flexible out of brittle material. And that's how we've done a lot of stuff in MEMS, out of silicon, okay? All right, so there we have a surrogate fold. There's other ways to do surrogate folds, but that's one way that's done out of a brittle material, okay? And do you remember our kaleidocycle here? Okay, so this guy is in paper, but now here is a kaleidocycle done in polypropylene. And so now we have a fully compliant mechanism with continuous rotation made out of polypropylene. Okay, so kind of freaky, but there it is nonetheless. Okay?
In that case, you have spherical joints.
Yeah, in this case, these are still revolute joints. This becomes Bricard 6R. Yeah, if I put a joint in each one of those, and with certain configuration there. So, okay, so here we have a what we call a Origami Waterbomb base. So this demonstrates a few things. Here it is with creases here. And then we wanted to see if it's rigidly foldable, meaning that all of the motion can happen with just the creases. So here you see something that was made with rigid panels with literal hinges. I mean, these are just door hinges bought at Home Depot or whatever. And then it is, well, okay, so it is rigidly foldable, but we don't really want hinges here. And so here it is with some surrogate folds. Okay? So we're going to take a minute, and we are going to fold an Origami Waterbomb base. And we're going to see something unique here. So rip that out. And so now you're going to fold it along those crease lines. And you notice this is also very symmetric. Okay, so you can fold these across there very easily. Okay, this is called a base because it is basically the fundamental unit that is used to create a lot of other origami, including what's called a Waterbomb, okay, which you can make and fold it up, fill it full of water, and it becomes kind of like a paper water balloon, as long as you can throw it before paper gets saturated. And it's also the base for like the origami bunny and a lot of other things, okay? So that's why it's called a base. Okay, when you get done, you should have something like this, okay? And so notice if we have all 8 of those creases folded, that it's not flat foldable with 8 creases. Okay, it's only flat foldable with 6. Why is that?
Because of the difference of two.
Yeah, it's going back to those theorems. 8's an even number, so that would be okay. But because of the symmetry here, we have to have the we have to have the difference of 2 between these. Okay. Okay, so I want to show something interesting here. So we've got it in this shape here, and it is what we call bistable, meaning that it will snap between 2 positions. That position, and then notice that it snaps over to the other position. Okay, so finding bistable systems is not always in compliant mechanism. It is something that we spend a lot of time doing. There's a very simple one right there. It's bistable. It snaps between those 2 positions. The problem is once you discover this, you'll find yourself in meetings folding these and snapping them back and forth. Okay.
And why is it bistable?
It's bistable. We've actually written a couple papers on this of analyzing the energy and stuff, and let's show that. Okay, bi meaning it has 2 positions where it's stable, and meaning stable 2 stable equilibrium positions, meaning if there's 2 points where the equilibrium or the energy is at a local min. Okay, so the energy is a local min there, and it's a local min there. I want to show you something freaky about this, though. In addition to it being bistable, okay, notice in this position, what is that, a mountain or valley fold?
A valley.
Yeah, it's a valley. Okay, now watch that valley fold, and it flattens out, right? And then when I see that motion, it's holding energy, or storing energy. It wants to go back to the position it was at. It was a valley before, and the other position, what is it? Still a valley. All of those positions, all those creases retain their own assignment. Okay? And if I rip off that vertex there, make a hole in it, it turns out it still does the same thing. But what's happening between those 2 positions is it's just stretching. You know how we'll model these sometimes is a hinge there with a torsion spring, right, to represent the resistance. And what's happening is I'm stretching that, really 6 springs here, stretching those springs, and then it wants to go back to its original position, and it does, but now it's in another configuration. So what happens is, what I'm hoping you're seeing here is even something that's fairly simple like this. Sorry, I keep messing up the video. Even something fairly simple like this has some fairly complex motions, okay, and some behaviors that are really interesting. So we propose this as the Waterbomb base as kind of a workbench or a framework for doing actuation. If you want to compare different actuation methods, you could actuate a Waterbomb base. So let's say I'm using shape memory alloy or whatever, right? Electroactive polymers, and I can compare those different things.
And the deformation of the torsion of the springs is in the same direction
Yep.
or in the opposite direction?
Yeah. So the torsion spring is going to be at this point its natural position. It just wants to be undeflected there, and then when I'm stretching it there, right, it's just storing energy. And since the angle is squared, it doesn't matter which way I go, whether that angle is positive or negative, because it's squared in the energy term.
But I agree that the energy depends on the deformation to the square, so the sign is not important. But it changed the rotation of the deformation?
No. Yeah, it just stretched it, and then it's a little bit, and then it snaps back to its original position. Yeah, which is non-intuitive, which is, yeah. All right. So there's some simple origami, but with some interesting things. And there's, okay, this field has only been touched just a little bit, okay? You have back here in the back, a professor at the University of Michigan. Raise your hand. Okay, that is also in this field, does some really interesting work in zipper tubes and other things. And there is, there's just a lot of other work that can be done here, especially in the kinematics area and everything else. So. Okay, let's look at some applications. First, let's start with looking at origami in space. So you have all the advantages of compliant mechanisms in space, where you can, reduce or eliminate things like lubrication, friction, backlash. We can dramatically reduce the weight, reduce the mass, which is a really big deal, and also, increase precision and so on. And then if we have origami in space, we have the big advantage of, all the advantage of compliant mechanisms, plus they can be super compact. You can have them be deployable, where they're compact in one state, right, and then deploy out to be large, be very compact for launch and deploy out in space. And then lightweight, I should say low mass. People at NASA always get upset with me. But anyway, low mass. So this is a satellite by the Japanese space agency called the Japan Space Flyer. And this right here has an interesting pattern. Those are not straight lines. Okay, this pattern was discovered by a man by the name of Koryu Muri, and that fold we call the Mura-ori. Okay, so in Japanese origami, okay, ori means fold, and kami means paper. So origami is folding paper. Okay, and so Mura-ori means Mura. That's the guy's name, and ori is fold. So it's Mura's fold. Okay, and he's a very nice guy. He's retired aerospace engineer now. We're going to fold the Mura-ori. Let's see. Can you guys hand out the Mura-oris? So it's in your packet here, but we're going to have to cut that out. We already have some that are cut out. So, we don't have the. Okay, you're going to fold this at home. Okay. You have the pattern there. There's two of them. If we have time, I have some scissors up here. We can, but not enough for everyone. So we'll let me show you what a Mura-ori looks like. This is a Mura-ori, but in nylon. Okay, and there you see the pattern. It's some people call it a herringbone pattern. You'll start to see this in a lot of places. It's just a beautiful fold. When you see pictures of this, it just makes it so you get, photographers love it because the shadows and stuff get on here. With this, we're looking at applications in nylon, things like, this is a deployable awning or a rain fly, right, where when that it deploys out, but then as it rains, it channels the water that comes down through there. But anyway, so very, very compact, and then deploys out and is large. Okay, so that's Mira Ori. Let's look at, let's see, remind me what time this session's over, so I know we've got quite a bit of time, but
This session ends at 12:30, so you have
12:30? Oh, all right. We can abuse you for even longer. Okay, all right, we got it almost now, so good. All right, so, okay, so we're going to look at a monolithic pointing mechanism next. This is something we did with NASA Marshall Space Systems. They wanted a 2-degree of freedom pointer that had plus or minus 15 degrees of rotation, no friction, no wear, had access for cables and fuel lines, and a low mass. And let me just explain a little bit more about what this is. So imagine this laser pointer. Let's say I wanted this, I wanted to automate this, and notice that dot on the ceiling if you can see it there. And I wanted to be able to orient it anyway in this direction, or anywhere combined, okay? But I want to do this with a compliant mechanism. And so the great thing with origami is it's so easy to prototype. I go grab a piece of scratch paper out of the recycle bin, and I can prototype, okay? And so here's some early prototypes. Many of you will know Clemar Gosselin, and we were looking at his agile eye, mechanism here. And so you can go into paper, and then here from paper, then we went into Legos. So these here are really cool. We also have some compliant mechanism Legos that we've designed. So we can just go, we don't have a cool set like this. You have to go get the files off our website. And even you saw these are all Lego compatible too. These holes and everything, these Lego parts that go together. So, and then of course things like finite element analysis. And that is, and then we put it in a polymer, and then finally in titanium. So you can imagine 3D printing that in titanium. That's like $6,000. So this is why you like to work with NASA. It's like, oh, how about printing that for me? Oh, sure. But anyway, so that looks like a crazy beast, but every piece on that has a function. Okay, so let's, each one of these, see where these two beams are crossing each other? That's what we call a cross-axis fluxural pivot, where those beams cross. And if you look at it from a plan view here, you'll see, these all lined up in a line, or across here you'll see 3. Turns out those are surrogate folds, and when we're doing that in paper, we had to be able to make a crease in titanium, okay? We can't just fold it like paper, and so here we created, we showed one kind of surrogate fold, right, which was this beam folded back on itself, and here we have this other, these cross-axis fluxural pivots acting as a surrogate fold. So there's this 2-degree of freedom, so we need 2 inputs. There's one input, here's the second input. This is where we connect to the spacecraft, and that's where we attach to the output stage. In this case, we're designing it for a thruster, a low force thruster on a satellite. And so here we'll see an animation of this, and there's controlling a thruster. And then no bending, it's all bending motion. There's no pinch points, so the fuel lines, are going to have access there. And then off you go into the sunrise. This is some work that Jared Butler in the back here did with NASA JPL on some origami bellows for space applications. This is on a rover application with a drill where you need this to have some really big compression to contain the elements of the drill. You need to protect. Sometimes you're trying to protect what's inside of this from debris. Other times you might be containing the debris to protect your system. Here's another one. This is with asteroid redirect mission, where here's the bellows here. So one of the challenges with the asteroid, there's not a lot of gravity, right? So you come in and you have to grab a hold of the asteroid. It's hard to just land on it. And so here you have all these little grippers, and in this case, these little grippers are again compliant mechanisms in here. And then here's the bellows. And traditionally they're using these metal devices that are very stiff. This is still space grade material, but very packed, very, very easily compressed. So still flexible and what? You can't make things that are both flexible and strong. Thank you. Okay, so also this is one of the first things we did. This is with NASA's JPL and with Robert Lang, and we worked on a solar array where the goal was for that to create 250 kilowatts of power. To put that in perspective, that is all the solar panels on the International Space Station combined and double. Okay, so that's a large solar array. But to do that, you'd need a solar panel that's 500 square meters. To put that into context, if that were round, it would cover 5 lanes of traffic. Okay, so you cannot launch something that big into space. And so, but you also need this to stow into a standard launch vehicle. So here we're looking at the Atlas V rocket. So that was our container that we had to fit into. And this is showing a prototype here. This is fiberglass, Sterilite to simulate the solar panels. The flexible part in there is Kapton, the same stuff you use in your flex circuits. And here we'll see deployment. Okay, hope the rest of the videos work. Wow, I've not had this happen. Weird. All right, I'm going to restart here. Why don't you guys start passing out the flasher? Okay, you can go ahead and start folding this. We're going to see a mechanism that works well for this solar cycle. We'll see some reasons for that. have enough of those?
Yeah.
With the start.
Okay. All right, we're going to try this again. All right, so here's this prototype. This is 1/20th scale. Okay, this would be 20 times larger. There you see the motion. There you see the hole in the middle. And this is another way, a different way of doing a surrogate fold. So we call it membrane fold. So here you cannot fold fiberglass. And so you have this cap down here that is flexible. And notice that there's different gap sizes here, so between the fiberglass. So here you have some larger gaps, here's some smaller gaps. So you can imagine whether you have mountain folds or valley folds and a membrane over that, that's going to make a difference in how it folds. Okay, here's a video animation showing this in space. That hole in the middle is where you put the spacecraft, and this comes out and deploys. And so you see a very large ratio of its stowed to deployed area. And the original crease pattern of a flasher mechanism can look something like this, but then we have to modify it to accommodate the thickness. So we won't do that in the one that you're folding here. And then, of course, there's all kinds of math and stuff to make this work. And this particular one you can get on a website here. This is Robert Lane's Origami website. All right, let's go ahead and we can fold that flasher pattern, which we've already started. This is the hardest one of all the stuff I brought to fold.
Larry, I have a question about
Okay.
folding this.
Uh-huh.
So, is there a sort of a method to fold these things? Like in which order you should fold which pattern to make your life easier to these?
Yeah. So, so his question was about are there some tricks in folding this, and some of those are you'll see these lines that are lined up. Right, sometimes what I'll do is I'll fold both of these lines at the same time and just, use my thumb to crimp it at that vertex. And then I always, hey guys, can you give me one of those? Let me show you a couple tricks here. Thank you. So regardless of whether this is going to be a mountain or a valley fold, I'll always fold it in a direction that I can see the lines. Okay. And then, so that one, and then I come over and do that one again with my thumb and just go to the vertex. And then I also like to fold it back and forth because some of these are going to be valleys and some are going to be mountains. So I fold them all the same way, but both ways. So I would fold them all. I'd fold all the one on the horizontal and then all the vertical ones. And then the hard thing is the collapse. All right, do you remember the term we used was flat foldability, flat foldable? Okay, what was something that was flat foldable had what characteristic?
Should be.
Yeah, it could be folded flat in second position. You know it's folded, it's flat in its first position because it's a sheet of paper for crying out loud. Okay, so now the second position. This is not flat foldable. When we get done with this, the second position is not going to be flat, and it would have to be able to move through itself. It has self-interference. It would have to be able to fold through itself in order to be flat foldable. And there's, you know, these silly laws of physics that get in our way. So. And it turns out mathematically that those things are really hard to mathematically determine on the self-intersection and stuff. So. Okay, and there's an origami artist. His name is Jeremy Schaefer, and he's the one that gave this its name of Flasher. He's a little bit of a crazy guy, and so you'll see, you can go on the web and find some weird stuff he's doing with flashers and stuff. Okay, Brandon here has one to show you that's folded up.
With the
So watch.
size, you can see.
So where you're going there.
Kind of rolls upon itself once you have all the folds assigned.
These beams that I have on the way or on the heat. So I told them I just told all of this the same way. Because they're doing my theories and that. So that'll be so I have to leave that.
Maybe they'll just end up reversing it, but then
Okay, and that point where you have all the creases folded and then you're trying to get it into its final form is called the collapse. And that's where you get all right. How are we doing? I see a number of people with it. Okay. And so that one's a little hard to get there, but once you do, it's really cool motion. So it's kind of action origami, right? Because of the motion is what's important here. All right, you can keep folding. We're going to move on here. So I talked about origami in space. Let's look at biomedical origami. Okay, so this is what we call nano injection. It's important. Okay, so first. We have a little description here. DNA has a net negative charge. If we put a lance, but a positive charge, we can attract the DNA. If we put that into a mouse egg cell, while the male and female DNA are mixing, we can get the DNA to be taken up by the mouse egg cell. We put that egg cell into a surrogate mother, and that egg cell divides and becomes a baby mouse with her genes. So we collaborated with microbiologists on this. We're doing genetic research. This was a prototype. So now we're making stuff on a silicon chip, right, with things that are popping up out of the chip. Okay, so again, this is where the origami is coming in. We have some also a lot of flexibility going on here in silicon. That's basically glass. Turns out you can do that because you can make things that are both flexible and strong. And it turns out you can even make it out of a brittle material because brittleness is about how it fails, not about its flexibility. Here's an animation showing this, and it pops up. Turns out we needed high enough precision to not only hit the mouse egg cell, but hit the pronucleus within the cell. And so after you do that, you take that and go and plant it into the surrogate mother, and off you go. This is one where we place some of those hinge-like things with all compliance. You see that motion. This is another one for a contact lens dispenser. With a contact lens sits here, and as you peel back the foil on the package, it actually presents the lens to you. So your finger can just slip in underneath there. So here you see an animation of this, and it just deploys. And so again, you have a lot of stuff, a lot of folding of things going on here. This is something we did with GE Healthcare on a C-arm X-ray machine. And you see a modified Mira Ori, where here it's very compact. This is to keep the C-arm in a sterile field even as it's moving. and there's its halfway, and it's expanded, so it's kind of like a bellows, but it's not all the way around. So you see a very large difference between its intact state and its other state. This is a Tyvek, which can be, we can put in the operating room and stuff. I've also worked with a company called Intuitive Surgical that does the Da Vinci surgical robot. And here, this is a device we call the Orriceps, Origami-based forceps. We're going to fold one. Oh, you guys, do you mind passing these out here? This will be quick to fold. But watch this animation here. It'll come in, deploy, and be able to grab things here. So very compact. And here's an animation showing it in a surgery where you're retracting the liver. And get it out of the way so you can come in and do another cauterize in this case. And here were their devices, quite large. And then here was the device we were able to make, significantly smaller. In a minimally invasive surgery, the size means a lot. This is approaching the size where there wouldn't be any scar at all. But also notice this is the size of their wrist. And notice the size of the wrist there. So what is that smaller, tighter wrist? What does that mean? Yeah, a lot sharper turning radius, right? We're going to need a lot smaller workspace with this device than that device. All right, so let's fold these Orriceps. And does everyone have one? So now this is another one that is not flat foldable. Okay, it will not go into a flat position. All right, Brandon or Colin, why don't you show one up? Do you have one ready? So in the end, you should get something that looks like this. So you squeeze that middle. Let me show you something else here that's kind of cool. Is when it's coming in, you can do it so that it's flat like this around, or not flat, but around the cannula, the cylindrical part that comes in, and then gets inside the body, and then it's able to morph and do, and then be the forceps. Okay, so that morphing is also kind of a cool feature there. Okay, and oops, sorry. All right, so you just folded a compliant mechanism medical device, right? Prototype. So that is based on the chomper mechanism, which is used in things like, fold origami dinosaur or something, right? It has a mouth that closes. Now we had to modify it to do what we wanted to do, but still it was inspiration to that. So I talked about space, we talked about biomedical, and then there's also consumer products. Here's one that's backpacks. This is with our industrial design group. So here you see these tubes, and were prototypes of this backpack that she's designed here. And then here, this is what they call the tessel backpack. It's a tessellation, a repeating pattern. And this has no function really other than it just looks really cool. And of course, these industrial design guys know how to make stuff look cool. They call it the jetpack. They put it on Kickstarter. They more than tripled their funding goal and sold, thousands of these. And it was successful enough that other companies started to knock them off. Actually, so here's another one we did. What's that?
You don't have Kevlar backpacks? Kevlar?
Kevlar?
Backpack.
Yeah, we'll see some Kevlar coming up here, so not a bad time. Molded felt furniture. This is again with industrial design, but here I want to show because of this manufacturing method and because of the surrogate fold. So here he's got this felt, and then he's masking this in areas where he does not want it to stiffen up. He puts a resin along here to stiffen up these areas, and then he keeps some of these flexible. It folds up like that. It expands, and then there's the stool. Okay, so that's also shows the manufacturing capability. This is one we did with a local company that makes backpacking stoves, right? We're in the middle of the Rockies and a lot of backpacking outdoors. And the idea here is you put your fuel inside here, you could build a fire, small fire in your pot, boil water, or cook your dinner on top there. But then it also folds out that flap. And this is out of steel. We've done steel and titanium. It turns out, because you're going to put fire in there, it turns out you have very limited materials you can use. Okay? So, and here you see again our surrogate folds, what we call the ACT hinge, and the different components there. And whoops. All right, so there we've seen some examples of origami in space, origami in medical devices, origami in consumer products. And I'm going to show two other examples that really I don't know how to categorize other than they are weird and unexpected applications of origami. Okay? The first one is origami and freight locomotives. Okay? So it turns out that the aerodynamics of a freight locomotive are horrible. Okay, you would like to have a nose cone on a freight locomotive, but you can't because you don't know if that locomotive is going to be the first one or the second one or the third one or at the end. And when these are coupled together, locomotives, there's not very much space. An engineer has to be able to walk, the other kind of engineer, not the kind of engineers. Train engineers, they have to be able to actually step between the locomotives. So the ideal is to have a fairing that can deploy on front of the front locomotive, but then stow and be small when it's not. So here you see a prototype in steel. You see this folding out. And we have, again, a whole bunch of spherical linkages in there. And here's just CFD showing different configurations. Here's us demonstrating it on a locomotive. And do this in about 30 seconds. This video is sped up. But the constraints on this are really tight because, again, in the end when it's stowed, a person has to be able to walk through here. It's very compact. Well, the first time we went out with the railroad company onto the train tracks with these locomotives coupled, and I saw how little space was in there, and we'd already committed to doing the project, and I was like, oh no, what have we done? Okay, so, but this is probably our biggest piece of origami that we've done in an application. But this also, our CFD and wind tunnel tests show that this is going to save the company about $6 million a year in diesel. And it's not only the diesel savings for the company, but that means it's that much less CO2 that's released in the environment. All right, the second one, I promised you two weird applications. The second one is bulletproof origami, okay? And this one is a barrier. You see this high-speed camera used to show it capturing a bullet. Okay, very compact, and then it expands out. And again, here showing that we're able to take the hit and decrease. So figuring out the deployable systems and stuff. So paper is a great place to prototype. And so 12 layers of Kevlar, I promise you Kevlar. And here's a stop motion time. see the fabrication. Here's a police officer deploying it. It weighs about 55 pounds. And here you see kind of the mechanisms in the back that's keeping it up. And just kind of holds it up, kind of like an umbrella mechanism. This we designed with Homeland Security for a SWAT team for having 3 people, where you have 1 person on the side and 2 armed people on each side. And so this was just showing it with 1 guy. Homeland Security wouldn't let us include Homeland Security people on the videos for various reasons. But anyway, so that's, and here I have with me today bullets that have been stopped by origami. Okay, so it's kind of weird. Those 9mm 357 Magnum and 44 Magnum that we've tested it with successfully. Okay, now let's fold one of these barrier patterns. This, I think, is our probably the last folding pattern that we'll do. And some of the other you'll do is your homework. And this pattern is what sometimes we call a modified Yoshimura pattern. At 12:30, right? One thing I learned a long time ago as a presenter is never get in the way. We will not. I will not go past 12:30. So while you're folding this, just put in a plug for Brandon and Karen back here. They'll be presenting another device, origami-based device. We did for intuitive surgical, a different application rather than minimally invasive surgery. It's origami application on the outside of a robot. And for an application, we'll see that in student method robotics competition. So when is that tomorrow? 8:30. What's that? 8:30 in the morning on Monday. 8:30 Monday.
So I guess the big question is, how do we design these things?
Yeah. So in here the question is how do we design these? And so what we've been doing is, some of it is exploring the space of what the origami artists have done, and then each application we're going out and identifying different patterns, modifying those for the space. We published a couple papers in there, but that's another area. The actual design, that's wide open. So not only in the mechanisms, but in the whole design theory methodology or design automation, there's just tons of work in that area. There's not a lot out there yet on that right now. It's still, that part of it is still, kind of coming out, getting ideas for existing patterns. And this barrier pattern you're folding now, we've commercialized this. We're working on commercial. We've licensed the patents to a company that's working on commercializing it. But actually the pattern has changed some It doesn't take as much, hardware on the back side to keep it in its deployed position. Okay. So here's, can I see yours? Okay, so he's completed his here, the fast folder. Okay, and so you see it, comes up into a shape like this. Originally, we even had some more folds that kind of come around into a circle. It was actually the size of a spare tire. So we go in right into the car, into the trunk, and then you see the deployment, motion there. So, and if you go and fold that Miura-Ori, look carefully at that, you'd see, oh, hey, half of this looks like a Miura-Ori. The other half looks like a Miura-Ori. Looks like it's two Miura-Oris flipped around, okay, and connected in a weird way. Okay, we'll let you keep folding there, and then we're going to go through and see a few more things here. Okay, there we go. Okay, so the origami has some really interesting applications, right? We're seeing that what you also, the other thing you see is that there are a lot of wide open research areas as well. And so I've been showing you a lot of applications and things. We haven't gotten much depth in anything. The depth is actually in papers that we've published. So online, on the course materials, there's a list of our origami papers. So you can go and find those and get the depth that we didn't cover here. So I want to show you a related area. We're working in an area what we call developable mechanisms, which is a new topic. And here we're doing curved origami. Like here's an example of, if you see that shape, that kind of freaky shape, that's a design by Robert Lang called Elliptic Infinity. That company's just coming out with a lamp that actually has this shape based on his design. It's kind of cool. And but here we're doing membrane folds, okay, to get our motion. But when we were starting to work on the curve folding, we discovered that if we wanted to do this in rigid materials like this, that it was important that we put our membrane folds aligned with the ruling lines of the surface. Okay, so a ruling line, I just explained developable surfaces here. I take a piece of paper and move it into whatever shape I want without ripping or tearing or stretching, okay? If I do that, that is a developable surface. And a developable surface are also ruled surfaces, which means any point on this surface, okay, any point, I can take that point, and there's some point where I can take a ruler, and I can find a point where that ruler will lie flat on the surface, okay? That's the ruling line. And it does not matter. If I took a piece of paper and I didn't rip it or stretch it, I can take any point on there, and I can find that position, I can find a position where that ruler will lie flat, okay, period. That's a ruled surface. And those ruling lines, it turns out that if we take those ruling lines, and we take mechanisms and we align the hinges along those ruling lines, and we can have mechanisms there. And then you use this other property that we all know from rigid body kinematics, that I can have a skeleton diagram like this, but so long as this rigid link, it can be any shape you want, right? The motion, the kinematics are irrelevant. So once the kinematics are not affected by the shape of that rigid link, so long as it's rigid. Okay, so now I put these hinges along those ruling lines, and then I make the rigid link lengths, because it can be any shape I want. That would be the shape that conforms to that surface, and we could get mechanisms then that conform to the developable surface, and we call those developable mechanisms. So here you can see these mechanisms that conform to the surface and morph out. There are a couple interesting properties here. If I put it on a cylinder, and also what we'll call a generalized cylinder. In general, when you think of a cylinder, right, you think of something with a circular cross-section. A generalized cylinder is any shape where all the ruling lines are parallel. Okay, that's a generalized cylinder. So that is a cylinder, believe it or not. It's a generalized cylinder. Okay? And if we do that, if all the hinges are parallel, then the skeleton diagram is just a planar mechanism, right? It's a planar mechanism. On a cone, what kind of mechanism is this going to be, where all the hinge? Yeah, it's a spherical mechanism. We use some of this guy's work too in our work. So spherical mechanism there. And then this is a tangent developed surface, and we get a spatial mechanism. Okay? And here we see these, So then you can imagine all kinds of applications where now we can imagine mechanisms that can conform to surfaces and morph out of those surfaces. It's just kind of really interesting, right? So. Here's some surgical applications we're working on, where here you can see some scissors that are internal. But now I can have the mechanism that comes out, and because we have this hollow surface, or hollow cylinder, and it can come out, grab, as we're suturing, it can grab the suture and cut there. So, okay, here's one. Where we're using grippers. Again, it just morphs out of the surface, morphs out of the shaft. And here's my favorite, where we have these cylinders that can come out. So now same shaft, but now can morph out your cameras or lights or whatever could be there. And at the same time, have that, but still have a hollow tube where you can have your instrument come through. So you can have multifunctional devices. Okay, so I think this is another area where there is just lots of work that can be done on doing these development mechanisms. This just barely started, and so okay. So some of our outreach stuff. There's an app that's free on Apple, on iTunes, or Apple App Store, called Folded by You. Okay, see the double meaning, BYU. What happens when you let students do stuff, right? But this is a cool little app. It has some origami you can fold, and then it shows applications at the end. There's also a book called Why Origami. Again, it's kind of a double meaning, with Y is short for BYU, but anyway. It shows some of these applications we've talked about, but other things there. This is available. This was actually Amazon's #1 bestseller in origami for a little while, which I thought was really cool. And my kids just, Dad, it's origami. But it's still the #1, thing on Amazon. Yeah, it's just origami. I still think it's and then you see a bunch of videos and things. There you go onto our the website to find those. But the other thing is there's a lot of things, maker resources we put on Thingiverse and Instructables where you can go and make a lot of the things we showed today, like that 2-degree of freedom positioner and other things. You can go and download the files for free and make those. And of course, the academic resources of the book are compliant mechanisms. And I'd just like to acknowledge all the support and all the work. And of course, as everyone in this room knows, it's really the grad students that really do all the work. So, so that's great. And so thank you. So in your packet there's some other things we didn't fold. There's Mira Ori. There is a kaleidocycle. You want to fold one of those fully rotating devices there. And you can find lots of things on the web there. There's also another technique called one cut. If you fold this, follow these instructions, get a pair of scissors and cut across A to B, a 5-pointed star falls out. Houdini would do this, what he called paper magic. And you can do some really crazy shapes this way. I won't show you the simple one, but we have a couple on our website that are a little bit more sophisticated you can go and do as well. So.
All right, thank you. We have time for maybe a couple of questions.
Who is going to ask a question when lunch? I can hear lunch.
I have to give them that opportunity to ask.
It's a formalism.
Yes.
You're welcome to
All right.
copy.
Okay, all right. Thank you again, Professor Howell.